Video generation has advanced rapidly in visual fidelity, but how do you actually direct a complex scene? Imagine choreographing a chase scene. You need to carefully coordinate not just the runner's path, but the exact movement of the pursuing camera. The problem is, object dynamics and camera trajectories are inherently entangled. This brings us to the core bottleneck in modern generative models. If we try to solve this by predicting raw 3D coordinates, it fails because it's completely non-intuitive. Human directors just don't think in terms of raw mathematical vectors. But on the other extreme, standard text-only prompts simply lack the spatial reliability required for precise directorial control. And most importantly, you cannot treat them in isolation. A camera's movement is almost always defined relative to the moving object. You can't plan one without the other. To bridge this gap, we introduce LAMP, Language-Assisted Motion Planning. Instead of regressing raw 3D coordinates, we treat motion control as a language-to-program synthesis problem. LAMP leverages large language models as motion planners to translate your natural language descriptions into a structured, cinematography-inspired domain-specific language, or DSL. We give the LLM the ability to write symbolic motion programs, turning it into a virtual director. So, how exactly does this virtual director communicate? It speaks through our motion DSL. We built this language directly on top of real cinematography conventions established in previous work like CameraBench. We designed 4 core primitives. First is free form. This is almost directly equivalent to full 6 degrees of freedom control, allowing you to explicitly define translation directions and rotations for completely unconstrained movement. The other 3 act as highly flexible, rule-based presets designed around the subject. For instance, tail track is our general primitive for any following movement, whether it's a tail, lead, or side track. By simply passing modifiers, you can easily adjust the following distance, style, and tracking axis. Then we have the rotation track. This computes the necessary rotation to keep a moving object perfectly in frame. Whether the camera is fixed or moving on its own trajectory, this primitive seamlessly executes cinematic pan and tilt tracks. For circular motions, the orbit track handles both short arcs and full 360-degree sweeps. You can easily define a fixed or variable radius around different axes. Finally, completely orthogonal to these spatial primitives, we enrich the language with common stylistic modifiers. You can easily inject steadiness effects like camera jitter, or control the acceleration using speed and ease in modifiers. We comprehensively evaluated LAMP's performance across 2 distinct and challenging benchmarks, the DataDo-P and ET datasets. To quantify our results, we focus on 2 primary metrics. First is the F1 score, which segments the motion's translation and rotation to rigorously measure geometric accuracy. Second is CLR-TR, or contrastive language trajectory. Similar to how CLIP works for images, CLR-TR evaluates how well the generated 3D trajectory actually aligns with the semantic meaning of the text. Even without being explicitly trained on either of these datasets, our zero-shot DSL approach surpasses all current state-of-the-art baselines by a remarkable margin in both spatial accuracy and text alignment. To summarize, LAMP represents a true paradigm shift toward language-driven cinematography. At its core is our editable, compositional, and interpretable DSL. Instead of relying on black box predictions, you can iteratively refine and perfect your shots simply by talking to the model before committing to any costly video rendering. Because we completely decouple motion planning from pixel generation, LAMP serves as a highly flexible, plug-and-play interface. The explicit 3D trajectories we generate can be seamlessly used to condition various downstream video diffusion models. Finally, we achieve state-of-the-art results without any dataset-specific training. This strong generalization is made possible by our new high-quality, large-scale procedural dataset of 400K text motion pairs, which effectively teaches the LLM the fundamental grammar of cinematic motion. Thank you for watching. You can find the links to our code, pre-trained models, and dataset in the video description below. We look forward to discussing our work with you at our poster session in Denver.